Hey everybody, welcome to Fastware. Today we're going to be talking about assembly. Now assembly code is as close as we can get to machine code. And today we don't write assembly code directly. However, we use tools such as compilers to generate from higher level languages such as C or C++. There are others as well. Now, you might ask yourself, why do we want to understand assembly? Why do we want to be able to read assembly? And my answer is always because you want to verify the output of the compiler and to understand if the compiler generated a reasonable code for an algorithm that you're trying to implement. Now, compilers are just tools. So tools have bugs and they have mistakes, and some optimizations might not fire, and the assembly produced for a specific algorithm might just be absolutely terrible. A trivial transformation of exactly what you've written in your code, which is not what we want. Now, here on the screen, we're looking at the very well-known algorithm. And if you recognize it, please leave a comment on this video saying what algorithm this is. Now, we're going to be looking at few examples of assembly output today for exactly the same algorithm, for this algorithm specifically. And we'll be looking at how the compiler fails to generate good assembly even if you align your data correctly and structure all your C or C++ code well, the compiler still fails to produce efficient assembly code to solve this problem. Right? So, with this short introduction done, we'll be looking at the Pythagorean Theorem. Now, we all know Pythagorean Theorem, c squared equals a squared plus b squared, right? So, but to know the hypotenuse, you would want to do a square root of c squared, right? So that's very simple. So let's look at a trivial example. So we have a little class with a base, height, and hypotenuse. Providing you have a base and height, you want to calculate the hypotenuse. And we're going to be looking at calc hypotenuse function. Now, here is the trivial implementation of such function. The hypotenuse is equal to square root over base times base plus height times height. Very simple, nothing up my sleeve here. Now, this code that we just looked at is the actual output of this algorithm. So here I ran some benchmarks. And in perf, which we looked at last week, I'm looking at this function, the OOP triangle calc hypotenuse. Now, this is a very simple algorithm, and I'm sure you can understand. So the instruction, the v move ss, stands for vector move single precision value. So this is moving one float from the RDI register into MMX0 register. And the second instruction takes an offset of RDI, which is a pointer this in this example. So here is moving your base. The next one is move a single precision value from offset 4, so 4 bytes off the base, so that will be height, into MMX1 register. Now multiply the MMX0 register with itself and store the result back into MMX. So this is base times base. The next is multiply height times height and store back into a height register. Now next is add instruction. So vector add single precision. You multiply MMX register 1 plus MMX register 0 and store it back into MMX0. So what it does here is taking the result of base times base and height times height and adding these together. and storing this into a register mmx0. So this is the clearing instruction. It says basically clear the mmx1 register, so it XORs with itself with the result of that, which is 0. Now here is some error checking. It says now if mmx1 is 0, do some other code, but if it's not 0, continue with this particular instructions. So it does vector square root single precision for mmx0 register, which is where we stored the addition. So the addition was stored into mmx0, and this is what we're doing, square root off of that and stores there. And then the last instruction, it moves back from mmx0, so the result of the square root, into the offset 8 of RDI. As we looked before, the offset 8 is the hypotenuse. So it's very simple, right? So offset 0, offset 4, offset 8. And here we're storing an offset 8. So the algorithm here is trivial. It is very simple to understand. However, I think it's clear that the algorithm here, the compiler generated code for this algorithm is terrible, because it basically does exactly as you tell it to do, and there is no optimization here. And this is compiled with O2. The reason why compiler cannot do any better here is because your algorithm is just, your data layout for this algorithm is just not suitable for any decent optimization to fire here. Hence, the compiler just goes through and does the most trivial data transformation and fails miserably to do anything useful here. Now, I have a different implementation for this, and here I have calc hypotenuses, which is the data-oriented approach, and the data is stored in the SOA form. Now let's have a look real quick. At that implementation. So we have SOA triangle, and here we have a little implementation. Now, you might immediately say, whoa, that's something very different. And it's true. This is using the intrinsics. I have optimized this code by hand in order to produce exactly what I wanted to produce as fast as it possibly can. But before we'll look at the performance result of using intrinsics, what we will do is we'll just comment out this code, and then what we will do is we have a vector of floats, which is all the bases, a vector of height, which is just all the heights, and then what we do is we assert that they are exactly the same. We have a vector of hypotenuses, and then what we do is we iterate from 0 to the size, calculating the base, the hypotenuse for these bases and heights. Now this is a very trivial algorithm, and let's compile this and have a look what we'll get. Sorry. Let's build and let's run. So what we'll do is we'll just one.python. So here we're running, again, calculate hypotenuse for the same problem, but at different scales. So from 64 hypotenuse calculations to well over 250,000, and the object-oriented model and an SOA form. However, looking at these results, you can see that the SOA form, when you transform your data into vectors of data, actually takes longer than the object-oriented model. And here you say, haha, look, everything that you said about SOA form being better is wrong. Well, not exactly. So let's run a little bit of a perf to actually understand what is happening. So perf record -g. If you don't know how to use perf, please have a look at the previous video that I created on this topic. I'm teaching about perf stat and perf record and how to use these, and everything that was taught there will be used today to actually analyze this application. So perf record, the Pythagorean theorem. Let's run this benchmark, compute some data, all fantastic. It takes a while, as usual it does. Now after this is complete, which is almost is, we're gonna run perf report. So perf report -g. Now perf report takes in a file which was generated by perf record, which is called perf.data, and displays it in a call graph information. So here we have the calc hypotenuses function, which we have, and we want to have a look. So I will press A key to annotate. So here we have this function. So where we are, this is the beginning. So calc hypotenuses, and it does a lot of preparation. And then what it does move and multiply. But again, have a look at these instructions. Vector move single precision. Now this is not what we want. What we want is vector move PS, which is packed single precision. So packed, when it says packed, it takes the entire MMX register, which is 128 bytes in size, so it can fit 4 floating points in there, and pack all these floats together. And our data is packed closely, so we should be able to load them all together. But for some reason, our compiler just fails to understand this pattern that we calculate the hypotenuse here, and does, again, a very trivial transformation. It uses a single float from this vector instead of 4 of them or 8 of them. Now, this is terrible, and we don't want that code to go to production because, again, it is slow. We just don't want it to slow down our applications at all. So what we do? So what we will do is we will implement this algorithm by hand using the compiler intrinsics. So let's uncomment that code and let's step through this code to understand exactly what's happening here. So I decided to use groups of 8. So because I have a machine which supports the AVX extension on my CPU, which supports 256 bit registers. So in one register, I can pack 8 floats, and I can perform operation on all 8 floats at the same time. There's also registers for doubles as well. So, but doubles are larger, so you can in 256-bit register pack only only 4 doubles. So we don't have such a requirement, so we just use float and we pack 8 of them. So here is our main loop. So we do our base preconditions. We're gonna be iterating over 8 hypotenuse calculations at the same time. And here what we do, we load unaligned. So it says 256-bit register, load unaligned, packed single precision data. And we load bases. Now the next is again load unaligned packed single precision of all the heights into our A and B. Now A will be replaced by multiplying A times A, right? So that's your A squared. And here is multiply B times B, that's your B squared. So base squared, height squared will now be stored into A and B. Now we add A and B and store in this R register. So again, this is happening on all 8 values at the same time. And in this graph, you can see exactly how this is happening. Now, the last instruction here is, well, one to last, is the square root. We take the square root out of each value of R and store into the H register. And the last thing that we want to do is give a memory address to hypotenuse and store this H value into the hypotenuse. Now, this algorithm is generic. It doesn't have to be 8 aligned. So anything that is above 8 aligned, for instance, if you have 10 of them, so it will go through once and we'll do 8, and then the last 2 we'll just use the basic algorithm to perform the hypotenuse calculations. Now let's compile this code now and have a look at what assembly looks like. Right, so we compiled here. Again, let's do record. So the OOP compute hypotenuses look exactly as it did previously. So again, for 250,000, it takes about 1 millisecond to do this. These are microseconds US, right? But now let's have a look at SOA. This implementation is about 3 times faster at every scale of the problem than the trivial implementation with object-oriented model. I think that's a win. And we didn't have to do so much work to implement this. So now with perf report, let's have a look at what we have as an output. So here we have SOA calc hypotenuses, and here's the actual function. Now we're talking. So we do some pre-preparation here, and here we have vector move unaligned packed single precision data. Now this moves into bottom register, the MMX2, and then it extends that register into elongated the 256 byte register. So the upper bits is the YMM2 register. Now we do exactly what we would think. Now this extended register is YMM0, and then we multiply the value of YMM0 with itself. Now the next, so this is doing our base, these instructions right here. Now next is doing the height. So it says load the bottom bits, load the high bits, store everything in YMM1, and again multiply it with itself, and then we take the results of our base and our height, and then we add them together right here. So this is height, base, store in the YMM0. The last here is you do a square root and the result stored back into YMM0 register. The last few instructions here is to actually extract the values from So again, from the bottom bits and from the high bits, and just store back into that vector of hypotenuses, right, as standard floats. And some cleanup code for the loop so it can continue. So this is just a short introduction to assembly and compiler intrinsics. I hope you found it useful. And if you want to see more of this, please subscribe, like this video, and I'll see you in the next one. Thanks.